Good afternoon, good morning, good evening, everyone, depending on where in the world you're joining us from. My name is Jarka Glassey, and I'm currently holding the role of Vice President Executive of the European Federation of Chemical Engineering, EFCE, having started my second term in January 2024. I'm a biochemical engineer by training, graduated from Slovak Technical University in Bratislava, Slovakia, although I worked all of my professional career in the UK in Newcastle University as a professor at the moment. I work mainly with biopharma companies using AI and machine learning methods for process development and optimization. But our group have applied hybrid modeling methods in areas such as catalyst development and other areas relevant to this particular webinar. So I'm very happy to be involved in the introduction of this webinar on application of artificial intelligence to chemical reaction engineering and process intensification. And I'm looking forward to hearing all about the exciting new developments in this area. Let me just say a few words about this webinar series. EFCE is organizing a series of virtual talks on timely topics in chemical engineering. This is actually now our 5th year of initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced the management of EFCE to transform the Spotlight Talks into a regular feature of our program. And this time round, we've got 10 of our working parties and sections delivering over 2 weeks, short sessions of 3 or 4 talks focused on specific topics by leading industrial and academics experts. The series also enables attendees to sample developments in areas that they find interesting, but may not otherwise have had the opportunity to attend before. In this way, we want to encourage cross-fertilization between specialist areas. Links to the next talks will be available just where you registered for this event and also via EFCE website. And as usual, we are recording the presentations and those will be again available via EFCE YouTube website. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 of chemical engineers in Europe. The working parties and sections of EFCE cover all major specific aspects of chemical engineering and are, in fact, the core of the organization, forming the scientific engine that drives many of our activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. I'm particularly happy that in this series of Spotlight Talks, we will have the first contribution of the 2 newest sections of EFCE, Chemical Engineering as Applied to Medicine and the Early Career Chemical Engineers. Before I conclude my introduction, I would like to thank all the people who worked hard within the working parties, sections, and EFCE in general for this initiative to happen and to be successful. In particular, many thanks go to EFCE's Martin Koo from Toulouse. Thank you, Martin, again, who did most of the conceptual setting up and practical activities, and without whom none of these spotlights would be the success they are. So thanks again, Martin. I thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. And I'll hand over to the chair of the Process Intensification Working Party, Professor Georgios Stefanidis, and also the chair of the Chemical Reaction Engineering Working Party, Professor Kevin van Heem, to start the works. Thank you.
Yes, thank you very much, Jarka. Hello, everyone. I'm Georgios Stefanidis. I'm the chairman of the EFCE Working Party on Process Intensification, which currently comprises 27 members from industry and academia across Europe. First of all, I would also like to thank you for participating in this webinar, both the speakers and the audience, and particular thanks to Martin Koo for taking on the organization of the webinar and for disseminating all relevant information. The webinar of today is the second joint effort with the CRE Working Party, the Chemical Reaction Engineering Working Party, over a period of 16 months, I think, which basically shows our common ground and our common interests with the Chemical Reaction Engineering Working Party. Professor Van Heem, the chairman of the Working Party of Chemical Reaction Engineering, will talk a little bit about their activities. I will talk a bit on the PI Working Party, the Process Working Party. For those of you that are not familiar with the term or with our activity, processification typically involves development of novel equipment, processing techniques, and operational methods that in principle can bring about significant benefits in chemical process industry in terms of resource efficiency, both materials and energy, efficiency, reduction in plant size, and a reduction in environmental impact and overall process economics. The mission of our working party, of the Process Intensification Working Party, is to disseminate knowledge on PI and promote PI in education, research, and chemical industry in Europe. Also, given the fact that the field itself is dynamic, we're always looking for ways to modernize it. And in this regard, the subject of today is very relevant as artificial intelligence has well penetrated into the field of chemical engineering at large, and is increasingly being used for process and product optimization. Particularly when it comes to processification, I have to say that the technical solutions that are usually put forward are usually quite more complex compared to conventional ones. And therefore, often comprehensive knowledge on the interaction of physics and the chemistries involved, and physical models are missing. Comprehensive physical models are missing or are not sufficiently developed. And on these grounds, I believe that AI might have a significant role to play in process optimization and control, and even in terms of unveiling some new physics, aside from its obvious merit of reduction of computational cost. So the webinar of today has a total length of approximately 2 hours. If you look at the program, in lieu of us focusing on a particular subject, we try to bring some diversity and touch upon different interfaces of artificial intelligence and chemical processing. To that end, we have invited 4 young and very knowledgeable speakers, 3 of them from academia and 1 from industry. There are 30-minute slots reserved for each talk. We have asked the speakers to conclude their talk within 25 to 27 minutes, so there are some minutes left for questions. Those of you that will have some questions while hearing the presentations, please type them in the Q&A box. And at the end of this presentation, either myself or Kevin will transfer them to the presenters, will ask them to the presenters. So that's it from my side. With that, I would like to conclude and give the word to Professor Van Heem.
Thank you, Georgios. First of all, thanks to Martin and Jarka for organizing this. It's a great pleasure, and we see that there's a very wide attendance, so that's always a very good sign. You can see that we have an impressive list of speakers. I could say top of the world from all continents, so that's great to see. So also for the field of chemical reaction engineering and for our working party, AI is of course very important. And the future of chemical reaction engineering is poised for a transformative leap with the integration of artificial intelligence. AI technologies hold the potential to revolutionize various aspects of chemical reaction processes, from optimization and prediction to catalyst design and process control. By harnessing machine learning algorithms, AI can analyze vast data sets to uncover intricate relationships between reactants, products, and reaction conditions. This capability enables virtual experimentation, significantly reducing the need for costly and time-consuming trial and error in the laboratory. Moreover, AI-powered simulations allow for the exploration of diverse reaction scenarios, facilitating discovery optimal conditions for desired outcomes. As AI continues to advance, its integration into chemical reaction engineering promises unparalleled efficiency, sustainability, and innovation. By leveraging AI technologies, chemical engineers can unlock new opportunities for process optimization, catalyst discovery, and sustainable production, paving the way for a more efficient, environmentally friendly chemical industry. So I really hope that the speakers can illustrate all these aspects. And I hand over the word to Georgios to start with the introduction of our first speaker.
Yes, thank you, Kevin. So our first speaker today is from the National Technical University of Athens. He's Michael Michalis Kavousanakis. He's assistant professor at the School of Chemical Engineering of NTUA. And he will address the first topic of the webinar, which is on the interface of artificial intelligence and catalysis, specifically the talk of presentation of Michalis's programmable catalysts, algorithmic optimization of periodic steady states for enhanced productivity and selectivity. So Michalis, the floor is yours.
Thank you, Giorgio. Hello, everyone. It is my pleasure to be part of these EFCE Spotlight talks on the application of AI to chemical reaction engineering and process intensification. I would like to thank the organizers. Special thanks to Georgios for this invitation and all of you for being here in this session. So the topic of my talk is programmable catalysts. And I will be talking about algorithmic approaches, some old approaches and some new from machine learning that can help us optimize the performance of heterogeneous catalysts for better productivity. Heterogeneous catalysis is an integral component of many industrial processes, manufacturing food, materials, energy, pharmaceuticals, and this is due to several key factors, including the enhancement of efficiency, facilitating faster reaction rates, higher yields, the higher selectivity, which enables a precise control of the reaction selectivity, allows the production of desired products, minimizing unwanted byproducts, the versatility, where heterogeneous catalysts are adaptable to a wide range of reaction types and allows their application across diverse industrial sectors. The environmental impact reduction, catalysts hold a crucial role in pollution control and environmental remediation, with examples found in catalytic converters in automobiles. The waste minimization, where we use catalysts to allow for the conversion of waste streams into valuable products or intermediates. And of course, the overall economic impact, where by enhancing the process efficiency, reducing the operating cost, the development of new products, new markets for contributing to economic growth and prosperity in general. So what we want to do is we want to design faster heterogeneous catalysts. And to do that, we need to take into account the constraints that are set by surface chemistry and equilibrium. In particular, we have the Sabatier principle that states that the surface and surface adsorbates interaction has to be an optimal amount. Let's take, for example, here a simplified surface catalysis model of a species A that binds on the active sides of a catalyst surface, and upon adsorption, it reacts to produce the product B star, which is bound on the surface, and then this desorbs on the gas phase. Here, all kinetic parameters are a function of binding energies between the catalyst and adsorbates. And we notice that when the interaction is weak, the reaction becomes a limiting process because the amount of A that needs to get adsorbed on the active sides of the catalyst is small. On the other hand, when the binding is strong, we are here, then the reaction between adsorbed species is promoted. However, the overall rate is limited by the desorption of species B. This means that there exists an optimal binding interaction that gives the maximum catalytic rate, And the peak here shows the transition between the rate limiting phenomena. This trade-off is usually illustrated with the so-called volcano plots and implies the existence of an optimum catalyst that is best suited for each reaction when operating at steady-state conditions. Here on the right, we have an example of a volcano plot showing the performance of a fuel cell cathode as a function of the binding energy of oxygen, with platinum catalyst providing the best trade-off of binding energies. We need to take into account that the Sabatier principle holds for stationary equilibrium conditions. So, one method to improve the performance of catalytic reactors introduces the periodic behavior of controllable reactor parameters. In particular, we can achieve higher performance by oscillating the feed concentration, the temperature, the pressures, the flow, and such improvements have been observed experimentally and validated in some cases with mathematical models. And more recently, there are new synthetic capabilities which have allowed for the controllable variation of electronic states of catalysts themselves, as opposed to the variation of reactor operating parameters. And these programmable catalysts can be continuously perturbed, and using appropriately designed programs, we can optimize their catalytic performance in terms of both rate and selectivity. And examples of such periodic perturbations include the dynamical strain, where tensile or compressive strain yields physical and electronic rearrangement leading to variable adsorbate binding energies, the light illumination that separates the charge on the active side. And another example is the direct condensation of electrons in a catalyst within a catalytic condenser. This graphic on the bottom left shows a schematic of an ultra-thin catalytic film of amorphous alumina, 4 nanometers width, which is integrated into a catalytic condenser device that enables a tunable depletion of electrons from the alumina layer, and that this results in higher acidity of the catalytic layer. These methods have demonstrated the ability to modulate the binding energies of molecules on surfaces by a fraction of an electron volt, and this leads to new possibilities for oscillating the reactivity of molecules on surfaces as fast or faster than the static turnover frequency. For example, the surface of a catalytic condenser, as this shown here, has been shown to oscillate as fast as 3 kilohertz. And at these high frequencies, simulations of simple chemistries have shown that the oscillation between the two sides of the Sabatier volcano can achieve catalytic rates that are orders of magnitude higher than the Sabatier optimum. Now, if you take a look on the top left diagram, one can see the energy diagram for two stages. The red one, stage R, this corresponds to high binding interactions that favors the reaction between adsorbents A star and B star. This state stands on the right side of the Sabatier volcano, and there is also a blue stage with low binding energies that favors the desorption of products. Now, when we appropriately oscillate the binding energies between these two stages, in effect, we create a molecular pump that initially favors the reaction rate, and then the desorption. And we do that in a continuous manner. So we can make catalysis dynamic when we introduce an external forcing in the relative binding energy. Here, the forcing function in the middle of the slide is a step function and is parameterized by its frequency, the duty cycle. This is the fraction of the period at which we are at stage R, for example, here, the amplitude, and the lower endpoint UL here. And by repeating the step forcing function and enforcing oscillations between the two stages, R and L, this leads to oscillations of all chemical species. And here the figure on the bottom left shows the time series of coverage of species A, this is the black line, and the coverage of empty sites, this is the green line and dashed green line. And we observe that the coverage oscillations are in synchrony with the binding energies oscillations. Here the red color denotes the oscillation stage R. On the right of the slide, we present the limit cycle representation of the time series. Here we have the points here on the limit cycle on the black line. The dots here are separated by a fixed time step, and the different coloring represents the net desorption rate of product B. We have higher desorption rates observed at the left part of the limit cycle, left and top part of the limit cycle, and lower desorption rates observed at the right part, low and right part of the limit cycle. And we also have these blue and red stars that correspond to the static condition of states R and L. Now, in order to compute the optimal frequency that gives the highest overall rate, we need to compute these periodic states in a systematic way, and one can do brute force direct integration of the model that describes the system until it converges to a stable periodic oscillation. The term periodic steady state here denotes the periodic solution of the forced problem. This must have a period that is an integer number of the period of forcing. As an alternative to direct integration, one can solve for the limit cycles as a boundary value problem in time. And to do that, we use Newton's method. And now what I'm going to describe is the computing tools that can efficiently calculate the response of programmable catalysts to external periodic forcing, and using these tools, how to systematically explore the different forcing protocol parameters to understand their effect on the catalyst response. Now, let's say that we have a system of ODEs, ordinary differential equations here, that describe the dynamics of a catalytic reaction. Here, X, the bold X, denotes the state vector, the coverage of species, the reactant species, the partial pressures. The bold P corresponds to the parameter vector, the parameter of the forcing protocol. And now to compute the periodic steady states, we need to compute fixed points of the stroboscopic map. This is how we call it. This parameter here, S, which maps an initial state, which we find at time 0. And this is mapped onto the state observed after one period, the T capital. So when the initial state and the final state coincide, then we have a periodic steady state. And this suggests that we want to find the fixed point of this stroboscopic map. And we can accelerate this computation by applying Newton's method. This, of course, requires the computation of some numerical quantities like the Jacobian matrix, the monodromy matrix. This is partial S, partial X, which basically denotes the sensitivity of a stroboscopic map on different initial conditions. And in fact, the computational savings of this Newton method compared to brute force integration are significant. And we can reach up to 1,000-fold acceleration for the computation of a single periodic steady-state solution. Of course, all these computations of monodromy, Jacobian matrices, all these numerical quantities can be costly, especially when we have a high-dimensional periodic steady-state problems. But here the remedy is to apply what we call matrix-free Newton GMRS methods. Now, with an efficient solver at hand, we can perform now parametric continuation, continuous solution branches, approximate solution surfaces for different forcing parameters. Here we apply our methodology for a slightly more complex catalytic reaction network. We have a parallel reaction pathway with a 6-dimensional state vector, six variables. And as a metric of the solution, we choose the turnover frequency of species A. Again, we parameterize the step forcing function. This time, we focus on the best combination of frequency and the duty cycle. We perform again periodic steady-state computations on a coarse grid of one parameter continuation branches. And here the solution surface illustrates the turnover frequency of species A for each pair of frequency and duty cycle values. Now, what we observe is that the maximum is here, colored in red, and we get the best turnover frequency, the best performance of the catalyst for a frequency of 1,000 Hertz and a duty cycle approximately equal to 0.8. And here on the right side of this slide, we have the shape of the forcing function on the right, the shape of the forcing function. Now, the question is whether we can further accelerate this process without the need to perform all these time-consuming grid search computations. And this is where new algorithmic approaches come into play, adapt ideas from machine learning algorithms, and more particularly by adapting the Bayesian optimization algorithm. Now, our goal is to maximize the turnover frequency here. This is computed by performing Newton's method for periodic steady-state solutions. And to do that, we perform a Bayesian optimization. So Bayesian optimization is a method suitable for expensive, noisy, black box objective functions. And its success lies in employing a smooth surrogate model as a prior. Here we have a Gaussian process. This produces the blue lines. It's a process that can feed the data and quantify in the same time the uncertainty of unobserved areas, and can be used to make informed suggestions of where an optimum might lie. And this surrogate model gets continuously updated and improved with each Bayesian optimization iterate. So for each Bayesian optimization iteration, what we do is to optimize an acquisition function, A of X, here. Choosing this acquisition function allows the tuning of the exploration and exploitation trade-off. In simple words, the acquisition function looks at the surrogate model and determines areas that are worth exploiting, that is, points where the surrogate model predicts a maximum value here, and areas that are worth exploring, areas with large uncertainties. So the bottom figure here shows the acquisition function. This guides the Bayesian optimization regarding the best candidate point for an objective function. And here the acquisition function is the upper confidence bound acquisition function, which is a weighted sum of the expected performance that is quantified by the mean mu of x of the Gauss process and the uncertainty sigma of x that is also captured by the standard deviation of the Gauss process. Now, increasing the parameter lambda, this is the weight of the uncertainty. This rewards the exploration of the currently uncharted areas in the search space. Now, just to remind, each data point that is used for the Bayesian optimization is a periodic steady-state solution, which, as discussed before, can be found with the Newton's method. So this means that in order to compute a data point, we require an initial guess for Newton, and let's call this X star. For such problems, Newton's convergence is highly dependent on the initial guess, especially when the state is high-dimensional. And here we proposed a solution which provides a good initial guess using, again, Gaussian processes as a regression model. In particular, we construct an initial guess using, again, a Gaussian process, surrogate, a regression model, but this time for the solution surface, the state vector. We have an initial sample of data points of turnover frequencies corresponding to a specific parameter value, frequency and duty cycle, and their state vectors x. And then we apply Bayesian optimization to provide the next guess for the parameter set, P nu, that will produce the maximum turnover frequency. And to find an initial guess for this P nu parameter, we want to predict an initial guess, and this is done by performing Gaussian regression. Upon convergence, we update the two Gauss processes because we have one for the parameters space and one for the state space. And we call this process a Bayesian continuation. We have formulated this Bayesian optimization problem with Bayesian continuation for the parallel reaction network system shown here. And we computed again the maximum turnover frequency, which is 107.4 1/2. This agrees with the continuation results. And we also plot the optimum shape of the step forcing function, which is on the right end of the slide. Also, notice that the turnover frequency is orders of magnitude compared to the optimal static steady state. For steady state, it's the maximum that we can get is 3.8 on 1/2. Now, to understand the existence of an optimum in duty cycle with respect to the duty cycle, we observe the existence of a trade-off between the duration of the adsorption reaction phase, that is phase R, and the desorption phase, phase L. The right figure here shows the turnover frequency of species A by changing the value of duty cycle phi. When we have lower values from the optimum, this is the green line here, we can see that the overall turnover frequency ends being less at the end of the oscillation. And for larger values, this is the orange line here, we see that the adsorption of A decreases by a little amount, but from a lower starting point if the phase switches too late. So the overall average turnover frequency ends being less at the end of the oscillation. Now, so far we have optimized the shape of the step forcing function within a 4-dimensional family of step functions, and it is possible to further vary the forcing policy shape and thus add degrees of freedom to the optimization, of course at the cost of increasing the overall complexity and enriching the resulting optimization possibilities. And this can be done by considering a new set of basis functions that can parameterize many shapes. And for example, here we use radial basis functions, RBFs. So what we do here, we attempt to improve further the optimum forcing function, which we found with Bayesian optimization, by adding a single radial basis function on the L stage and optimize its shape. And we managed to further improve the turnover frequency by another 5%. And here the naturally arising question is whether this increase is due to the extension of the residence of dynamics in the R stage. And this is not the case. Here what we did is to extend the R stage of the optimal step forcing function by the duration of the additional RBF pulse. And we see that the turnover frequency gets a little bit worse. All parameters here are fixed except for the duty cycle, which is incremented by the duration of the RBF. This means that it is not simply the extension of one of the two stages, but it is the shape of the forcing function that leads to a better result. And here we show a projection of the limit cycle plotted for the desorption rate of species C. This is when we apply the optimal step forcing function. This is the blue line, and the red line is the optimal step plus the RBF. As expected, these two cases have similar dynamics most of the time. And in the case of the optimal plus RBF shape, what we observe is that the red limit cycle suddenly diverges from the first limit cycle and adds a new phase space loop. In other words, the additional RBF prevents the limit cycle from spending useful time in an unproductive state and kicks it for a short time to a producive one. The insert here shows the limit cycle behavior just before the phase change. And as you can see, the red line, the step and plus RBF spends less time on the slowest manifold. Now the target is to move on to more realistic, more complex catalytic systems with catalysts that can undergo periodic perturbations. Here we have a microkinetic model for ammonia synthesis using ruthenium as a catalyst. This catalyst, as you can see here on the volcano plot, is close to the volcano peak. And what we do is we perform periodic perturbations, in particular strain perturbations, and one can show from simulations that we can improve indeed again the catalytic performance by orders of magnitude. Again, to compute the optimal frequency of the step forcing function, one can resort to brute force integration methods, or apply Newton methods with significant, again, computational gains. Here we apply the Newton-Krylov method, this matrix-free methodology. Since we have a higher dimensional ODE system, we have 16-dimensional ODE system. Here we have the Newton's method combined with the GMRS. This is the black box process here. This computes the turnover frequency for ammonia. And this is what we use within our Bayesian optimization and continuation computational framework in order to discover the optimal strain schedule. Here we have fixed the strain perturbation to ±4%. And by performing Bayesian optimization, here we performed 11 iterations. We managed to compute the optimal oscillation frequency, which is around 250 Hertz. Programmable catalysts have the potential to improve the performance of catalytic reactors and facilitate the transition to efficient, sustainable production of valuable chemicals. I've shown you a method to combine scientific numerics with active learning schemes, machine learning schemes, Bayesian optimization with Bayesian continuation. We managed to efficiently compute periodic steady states and also optimize their performance. And some new exciting research directions arise, of course. The efficient optimization of more complex and realistic kinetic schemes, like the ammonia or methanol synthesis, with reactions that occur on multiple surfaces, molecules that can decompose or form through multiple pathways. It is also interesting to explore diverse optimization objectives, multi-objective optimization, where we simultaneously maximize the production rate and selectivity. Another area is the multi-fidelity in Bayesian optimization, which is a fascinating prospect. This combines lower accuracy, lower fidelity computational results from first principles models with accurate but costly experiments. And the goal is to converge towards a global minimum at a reduced cost. And the next frontier is to program not just temporally, but spatio-temporally catalysts. The local catalyst addressability will allow us to optimize not just the kinetics, but also the interaction of kinetics with transport. And with this, I would like to end my presentation, thanking my collaborators, Yannis Kervekidis, professor at Johns Hopkins University, Professor Paul Downhower, who's at the University of Minnesota, and Dr. Xiouras, who is currently working on for Sanofi. And if there is time, I will be happy to take any questions you may have. Thank you very much.
Yes. Thanks a lot, Michalis, for this very interesting presentation. I see there was a question posed during your presentation. The question is, I suppose that the S principle assumes that we know what the active species are, correct?
Yes.
Because that may change from catalyst to catalyst.
Yes, of course.
Yeah. Let me see. Let me quickly check for other questions. No. Michalis, if you are to talk with an experimentalist like me, right?
Yes.
So based on this theoretical work that you have carried out with your collaborators, what would be the message for me, let's say for the ammonia synthesis reaction? What should I do exactly in the lab? First, to validate your predictions and to optimize the production rate of ammonia.
Of course, there is the first step to build a model that simulates the dynamics of your system. You first do some simulations and see if the results are comparable accuracy. And then I think that the most interesting prospect here is that to use this multi-fidelity Bayesian optimization that combines model results and experiment results. So you can do some, if your experiment allows for perturbations of your catalyst or perturbations of your reactor parameter space, then we can combine the experimental findings with some computational findings to seek for a new optimal parameter set.
Now, I mean, what should I vary experimentally? What parameter? How can I reproduce, let's say, your predictions in the lab? How should I operate my system?
Okay, this particular work is about performing periodic, some periodic perturbations. This depends on the system. You may vary, for example, the fit composition of your system. You may vary the temperature. You may vary the pressure, and see if these variations produce an enhanced performance of the system. Or you may use all these new catalysts where you vary their electronic states. If you can do that in your system, then you can vary the electronic states of your system. Here, for example, for catalytic condensers, you switch on and off voltage, and you modify the performance of the catalyst, the binding energies of the catalyst. If you may do so, then we can have some, comparable conditions. I don't know if this answers you.
Yeah, I think I understand. Yes, thanks a lot, Michalis.
Thank you very much
for this presentation. I'd like to give the word to Kevin. We change subject. We change speaker and subject. Our next speaker comes from industry. It's Dr. Christos Xiouras, who's a senior scientist in the R&D of Janssen Pharmaceutica in Belgium, near Antwerp. Christos has expertise in crystallization, and he holds a PhD in crystallization, focusing on separation of enantiomers. In the presentation of today, he's going to give us a small overview of opportunities for enhancing, intensifying crystallization properties processes using artificial intelligence and machine learning. Christos, the floor is yours.
Hello, everyone. Good afternoon. Thanks for the nice introduction, George, and many thanks to the organizers for organizing this nice webinar. I'm excited to be here today to explain and present some of our recent research on modeling digital design of crystallization processes with some emphasis on statistical learning and basically machine learning techniques. As George mentioned, I'm a senior scientist within Johnson & Johnson Innovative Medicine, and I'm particularly, oops, it's not moving. Yeah. Working in the chemical process R&D, which is part of the therapeutics development and supply. And in this high-level slide, you see a little bit the scope of our department. So we start with a number of synthetic steps. So we take raw materials, we convert them into intermediates. Those intermediates are in turn converted into active pharmaceutical ingredients, usually in liquid mixtures of impurities and solvents. Once we have selected then a solid form, then we have to develop crystallization processes, which are rather key as they are used to obtain high purity active ingredients. And then we have to do a number of downstream processes such as liquid-solid separation, washing, drying techniques, and formulation blendings to go into actually a drug product. So basically, we start with an active pharmaceutical ingredient, which is a molecule. We go into a material, a crystalline form, and then we formulate that into a drug product, which is something a patient can use actually. Today, I'm going to focus on crystallization processes, not only because this is the area in which I work.
Christos, we lost the sound.
Hello? Hello?
I think it works now, Christos. You were muted. Yes.
Hello? Am I back?
Yeah, you're back.
Yeah, we're gonna hear you.
Yeah, you're back.
Hello?
Yeah, it's okay, good. Yeah.
Hello? Am I back?
Yes. Yes.
I apologize for that. So I was saying that 80% of active pharmaceutical ingredients are produced in their crystalline form, and crystallization is in fact a complex and dynamic process. So we have several rate processes that are involved in solution crystallization. So besides the fundamental crystallization phenomena, which is primary nucleation and crystal growth, we also have other phenomena acting in particle populations such as agglomeration and breakage phenomena. All of these phenomena are influenced by the supersaturation in solution, by the hydrodynamics of the reactor, and also by the solvent composition. And ultimately, their interplay defines the solid product attributes with important attributes such as crystal size, distribution, purity, size, shape, and form. So the complexity here is that there is not enough scientific understanding into all of these sub-processes, which often prevents us from robustly controlling crystallizations or experimentally designing those. So we typically, within R&D in pharmaceutical industry, we follow an iterative optimization cycle where experimental testing is followed by sampling and analysis, which generates some insights, and then the cycle repeats itself. On average, a crystallization development project could easily last 1 to 2 years, where more than 200 experiments are being performed, generating more than 600 samples, the majority of which are actually solid samples, which need to be analyzed by a wide range of solid state characterization techniques. So one solution to that, and this is more in terms of intensifying R&D efforts. So we would like to advance our understanding and control of crystallization by developing predictive models and advanced control strategies. So how can we do that? Actually, so there's 2 ways we can go about that in modeling crystallization, and particularly also any other process for that matter. We can have a mechanistic or semi-mechanistic model in which the model is learned by the user. So we, based on the collective scientific principles and the knowledge on the process system, and typically used to construct causal pathway maps or explain phenomena or describe, for instance, the dynamics of crystallization. Could be, for instance, a set of differential equations aimed to describe the process, or it could be something completely different. For instance, first principles, quantum chemical calculations aimed to predict structures, for instance. The other approach is more to use statistical or machine learning techniques. And then in this case, the models learn based on the data themselves. And you have 2 approaches. So you have the supervised learning, where we have labeled data. And this class of models, this class of techniques are mostly used to develop input-output predictive models. And then you also have unsupervised learning, where we don't have a training data set, and we are mainly looking into exploratory patterns, finding exploratory patterns in the data. There's a wide range of problems that can be solved using these techniques, ranging from classification to clustering, regression, dimensionality reduction, and all of which are of quite importance actually to this field. We also have the opportunity for hybrid modeling, where the 2 worlds are kind of combined. For instance, a machine learning model can substitute for a mechanistic model, or a machine learning model can be trained on a mechanistic model as well. So these are some of the possibilities that we can that we've seen in the literature, and we recently reviewed some of those in our review, which is mentioned here. So we can use regression techniques to do a number of things. For instance, model crystallization itself. We can use this to predict physical chemical properties, and Martin showed some nice examples of that before. We also can use to extract useful data from process analytical technologies. On the other hand, we have clustering classification techniques. We can use those techniques to predict crystallizability behavior, or to treat high throughput crystalline material discovery data, or do data mining. So this is a bit long to cover in this talk, so I will focus mostly on the first three elements that are highlighted here and give some examples of our research within J&J. This is by no means a work that I've done on my own. So there's a number of people involved within J&J. And I'd like to highlight this project automation. It's basically a co-financing between J&J and Flemish Ministry of Innovation, FLIO, in collaboration with KU Leuven for a PhD program. And a large part of what I'm going to show was carried out by this this excellent PhD student, Gustavo Lunardon Quiló. So this is an overview of what I will be discussing today. So I will start by explaining what we have done on solubility regression models. Then I will move to chemometric models linking to the process analytical technology. And then I will finally conclude with crystallization process models and our work there. And then I will provide some high-level conclusions. So solubility in crystallization process development. So just a refresher, solubility, just the maximum amount of solid that will dissolve in a fixed quantity of solvent. It's a thermodynamic property, depends on solid form, temperature, solvent mixture composition, impurities, number of other things. But mostly interesting for pharmaceutical application is the solvent composition and temperature dependence, since most pharmaceutical crystallizations are a combined cooling and dissolvent crystallizations. Solubility is foundational for crystallization process development because it allows us to know whether we can actually apply crystallization or what will be the crystallization yield. But not only that, we can also use solubility data to correctly estimate crystallization driving force, the supersaturation. And the correct estimation of supersaturation is key in order to construct accurate crystallization kinetic models. Despite being foundational, substantial experimental effort is needed to measure solubility. So we typically need 10 to 24 hours per experiment where slurries are equilibrated and offline analytics are being taken for concentration, usually by UPLC techniques. While we can, to some extent, parallelize this with medium and high throughput experimentation, there's still substantial effort, let's say, devoted to this kind of measurements. So reducing the experimental effort while still maintaining accuracy is quite of importance to us. And one way to do that is to just measure solubility at a number of selected points and then construct a solubility regression model to model solubility at unmeasured conditions. But how to do that exactly, how we can build predictive models for solubility. So we've done some research internally within J&J to see what models can be used. So a number of models have been tested to our compounds, ranging from mechanistic to empirical ones. And we found that about 80 to 85% of our substances could be well described by the Van Hoff-Joyban-Acri solubility model, which is shown in this equation here. So this is a semi-mechanistic model. It's derived from thermodynamic mixing models and can describe both temperature and composition dependent solubility for up to ternary solvent mixtures. So it's a quite flexible model. In its fullest extent, fullest form has 15 parameters that need to be estimated from experimental data. But we found that it's quite useful to use. So this is an example of such a regression. So this is 107 data points in a binary solvent mixture. So here the solubility is a function of both temperature and the weight fraction of the solvent. And you see here the experimental data and the fitted model response surface, which in this case showed to be adequately describing the solubility data. But as I mentioned, so only 80 to 85%. So that still leaves out 15% of cases or 20% of cases where the model will not be good enough or that we can't find a good model to predict or to regress solubility. So we looked into whether we can use machine learning models or statistical learning models to substitute or to predict solubility. So we tested several machine learning models, and you see here the list of the 44 models that were tested in the end. Some of them are just variations using different kernels of the same classes of models. But we wanted to see for the same data set, for instance, that I showed before, so the 107 experimental data points, we wanted to see how these different models perform. And this is shown in this graph here. So on the x-axis, you see the absolute average relative deviation of the prediction against the root mean square error of validation for these models. So basically, the x-axis is a training metric, and the y-axis is a validation metric. So typically, and obviously, we want the machine learning models to be as close to this region as possible. And we see, though, a wide range of behavior. So we see that models are spread out. So there's no clear trend on which models perform better in this case. And just by changing the kernel, but sometimes you had a much better behavior for the same classes of models. But we found that roughly half of the models that we tested were in an acceptable, let's say, region in this graph. We looked into more detail in the top 3 models that performed the best in terms of this prediction against validation metrics. And in this case, we found that models based on Gaussian process regression performed the best for this case, with, of course, different types of kernels introduced. And if you compare them with a mechanistic model, we were excited to find out that we had an even better prediction from the mechanistic model itself. So this is the about 6% error for these models against about 10% error where we had for the semi-mechanistic Joyvan-Akri-Van Hoff model. So this got us excited. So these are easier to compute, easier to solve. So can we use these models further? But before we do that, we looked besides points metrics, looking how the models perform in the entire design range. And this is a data set visualization for the same data set of 107 points. So we see here in these colorful plots, the 95% confidence intervals of the prediction over the prediction itself for the 3 different machine learning models. And this is compared again with the mechanistic model. So what we see here in these patterns emerging is that the statistical learned models have very high, very low, confidence intervals close to where the data points are collected. But the minute you go to an unexplored area, so somewhere in between the data or here where the data are rather coarse, so the confidence interval of prediction skyrockets. So this is on average about double as the mechanistic model, which in the end raises some questions. So when is it worth to actually use these models? There is some uncertainty in the predictions involved. So of course, we're not saying here that these models cannot be used. It's just it's clear that these do not generalize well. And in order to have a similar prediction, we would need to collect a lot more data to make these models feasible. However, for some cases where our mechanistic models will not work, this could be possibly the only way around having a reliable model. Regardless of what model we want to apply, we have developed a workflow in which we are aiming in reducing the experimental effort in getting the best possible model out. So this involves several steps. So in first step, we have a screening design to see which models work. So we model that screening design basically. Then we perform an augmenting of the design. So we run a technique called optimal experimental design on the selected models. And we use this technique to generate new suggestions for new data points, actually. And then we collect those points and we model the entire data set. So I'm going to explain this optimal experimental design technique in the next slides and what we exactly do with this technique. So in this technique, we basically want to define a minimum number of maximally informative experiments. So we want to find basically the experiments that will give us the most information. And in this case, it's basically related to optimizing statistical criterion. And we are mostly interested on the optimal experimental design, which is identifying the set of experimental conditions that minimize the average variance of the model prediction. So this is based on the fact that the average variance of model prediction is not only a function of the experimental data variance, but it's also a function of how your design looks like and where exactly you're evaluating your model. So we basically use the model structure itself to generate a number of experimental points, which are the most useful and the most informative ones for this particular model structure. So it's a very interesting technique and quite generally applicable to many problems, for instance, also in reaction kinetics, but we used it here for solubility data set augmentation. An example of this approach is shown here. And this is another example where data points were collected for temperature and anti-solvent. And you see here that the original design of 72 runs, this is the relative variance of the prediction of the model. So these colors signify more variance. This is again matching the point where the data was more coarse. Running this technique, we get some machine-generated data points to augment this design. And by doing so, we are able to spread, not only to spread out the error to more uniform in the design space, but in general to reduce it significantly. So by 11% additional experiments, we get a 22% lower relative variance. Of course, somebody could argue that if you're adding experiments, you're always going to reduce the model variance. So we wanted to compare how this approach worked with random augmentation. So here we did 10,000 Monte Carlo simulations to determine random experimental points, again 8 points, and we augmented those and calculated how much better our optimal design is as compared to random augmentation. And in this case, we found that on average we were 10% better than random augmentation. While this may seem rather modest, we applied this technique to a number of other compounds, and we, especially for more complex cases where ternary mixtures are involved, we found that up to 200% improvement compared to random augmentation is possible by using this technique, with the average improvement being more closer to a 50%. All right, so I discussed a bit solubility models. Switching gears a little bit, I wanted to discuss chemometric models, and more relevant is what we do here with the process analytical technology, how we use these models. So we have the option to collect data in our reactors using process analytical technologies. These are typically probe type systems that are added in automated lab reactors at different scales. And most relevant for crystallization processes, we have probes to help us determine concentration. So these are basically based on attenuated total reflectance IR or UV spectroscopy. We also have Raman spectroscopy to determine solid forms. And there's a number of PAT tools used to determine properties of the solid phase, such as particle size, shape, solids content based on image analysis, for instance, or turbidity based techniques. So these whole techniques give raw data which are not directly usable. So these are time series of spectra. Images could be a series of chord length. So it's not that we can do much with these data in this raw form. So they're okay sometimes for behavior or visualization, if you overlay different trends. But we wanted to get more quantitative data out of this. Also, we have large amount of data that need to be treated somehow. So we used several techniques to get more out of these tools, and this is some unsupervised techniques that have been used, for instance, generative IR fingerprinting. So what we do here, we do not perform any calibration of these trends. So this is for IR. So we collect. So what we have done here, we collect reference experiments from the lab and tracking, for instance, a univariate peak in the IR spectra. We get a number of trends looking like that. We then model them by sampling between 17 common kinetic functions. So this here is not to gain any mechanistic insights, but basically to simulate the spectra to get a best fit that we can do. And then we use these models to generate thousands of simulated experiments. So to obtain what we call a fingerprint distribution, as shown here. So we have applied this, and then we can use it in the lab or in the plants, where we can overlay trends of batches of experiments as they happen. And that's what you see here. For instance, this is an on-target crystallization batch where desaturation kinetics are being tracked in real time, and this is matching what we would expect. Whereas we can easily, let's say, see outliers, for instance, when a batch is not performing as expected. So this is doing some things with without performing any calibration, actually, of the spectra. But in order to go to kinetic models for crystallization, we want to have a bit more of quantitative data. So we've used simple machine learning techniques such as principal component and partial least squares regressions. And we found that these techniques are quite versatile techniques. So to briefly explain for the people that are not very familiar, so this involves basically a dimensionality reduction step where the input variables are broken down in its linear form. They are broken down in components, which are basically linear combination of all inputs. And then these components can be visualized, for instance, as different directions of maximal variance in the data. So for a simple two-dimensional data set, principal component 1 will describe variance along this axis, whereas principal component 2, being orthogonal to principal component 1, will describe variance along this direction. And the whole idea when you're going from the dimensionality reduction to the regression step is to use, instead of using your inputs as the regressors for the response, you're using only the components to predict your response. These techniques are quite useful in spectroscopy, for instance, and I'm going to show a few examples where we successfully applied those techniques. So the first thing that we're interested using these techniques is to determine concentration during a crystallization process. And this is an example of a seeded cooling crystallization. We have collected mid-IR spectra, which in this case show variability both due to the temperature, but also due to the concentration of the API being depleted from the liquid phase. By collecting a number of training data and pre-processing them to crop insensitive parts, also with derivatization smoothing, we are able to perform calibration. We have to determine first the number of components that are best describe this situation. And we've seen that in many of the systems, the number of components will tend to match the number of things that are varying in your system. So in this case, we have temperature and concentration being varied, and we see that the components to explain most of the variation is just 2. So using these 2 components, we constructed a quite accurate PLSR and PCR models. Here you see the prediction against the observed against the fitted response, and we were able to apply this online for monitoring the concentration during crystallization. Here you see an example where the concentration with black here is the online concentration, and with blue here you see some the offline points that were taken, which show quite good match. Interestingly, also the temperature is part of the calibration that can also be predicted. Of course, it's not something we're interested here, but just a sanity check that the model is actually able to predict well. So this is useful information showing, for instance, that when crystallization starts, concentration almost reaches the solubility at the isothermal part, and then when we start cooling, the concentration nicely follows the solubility curve up until this point here. So this information is useful not only for determining the endpoint of crystallization, but also for feeding into kinetic models to derive crystallization kinetics. This is another a bit different example where we wanted to, so we had a different problem, again, infrared spectroscopy, this time near IR. So we wanted to control water removal from a solvent to avoid the formation of an undesired monohydrate phase. So in this case, we had offline sample, which was not feasible because the product was at high temperature, or the reactor was at high temperature, and the product would easily crash out at this case. This was a much more complex case where spectra were influenced actually based on the chemistry, water concentration, the quality and concentration of the material, quality of solvent, temperature, mixing, and a number of other things were actually influencing the spectra. Nonetheless, a PLS model was was constructed to link the IR spectra to water content using significant calibration points. You see here a number of PLS components were needed, again matching the higher variability of the spectra here based on different items. But in the end, the model was successful, had an accuracy of 98.9%, and could be successfully transferred and used actually in a commercial in the plant actually. This is a third example, this time looking into Raman spectroscopy. So the Raman spectroscopy is more sensitive to solid form, to specific lattice vibration. It's able to differentiate between different crystal structures. And this is an example where we wanted to control the crystal structures with the aim of obtaining an anti-pure compound of this intermediate, this chiral intermediate. So this chiral intermediate tended to form a compound where both enantiomers were present in the lattice, although we knew that there were 2 enantiomer structures of the same material that were possible to be obtained. So we looked into the phase diagrams for this system. We found that the racemic structure was more stable than one of the forms, but was less stable as compared to this form. So we wanted to know, can we use Raman to track this phase transformation in this complex system where also racemization was taking place with the aim of obtaining an anti-pure compound. So in this case, we again constructed the PLSR model based on 30 ternary mixtures of the 3 phases. Again, 3 components were used, matching what was varying in our system. And by using this model, we were able to obtain quite deep process understanding, which allowed us to obtain higher than 99% enantiomeric excess for that system. So we basically were able to design a semi-batch process where the racemic crystals were fed and in situ converted into the enantiopure phases. Interestingly, based on this information, we could infer the evolution of the enantiomeric excess in the solid phase by a Raman, which was then compared with the offline enantiomeric excess by UPLC, and we found a very good match. So this is quite interesting because there are no PATs at the moment that are able to give this information. Of course, it's indirectly here, but this is quite interesting because we can use Raman to fully automate this process. So we could use it as a control mechanism to have this well controlled, actually. This is the last slide on chemometrics. So we also want to go into more advanced techniques, and that is needed when, for instance, we want to gain more advanced solid state data from particle images, for instance. So we have a number of ways to collect these images. So we have static equipment, but we also have dynamic equipment where images are collected in situ. So a dedicated team within J&J developed deep learning models based on vision transformer to actually get some information from the images collected during these instruments. So based on that, two applications were designed. So first one is deep particle, which was aimed at treating static images. And as you see here, successful image segmentation could be applied, and the individual particles could be detected, and some size descriptors could be extracted using these models. However, when we went on to try to apply the same strategy for the online images collected from slurries, we saw that the basic functionality was there, but the actual segmentation was not that straightforward. So we saw that due to the out of focus images, owing to the dynamic nature of the slurries and the dense slurries that we have in our systems, that the algorithm couldn't really differentiate in all cases. We are looking forward, so this is work in progress. So we're looking more into improving these techniques, working also with the vendors of some equipment, because there's been quite some advances in image analysis for the past 2 years. And our aim here is to develop a source agnostic tool application to treat images regardless of where they come from, whether these are dynamic images or static images. But still work in progress here. A lot more developments are expected in this area. All right, that brings me to the last part of the presentation, where these two elements that I showed come together to design crystallization process models. So why would we want to perform kinetic experiments to design crystallization kinetic models? So we want to be able to describe and predict the crystallization behavior, but we also want to use these models to optimize and robustly control crystallization trajectories through the development of digital twins. This, we believe, will simplify troubleshooting and also support scale-up and tech transfer for our processes. How does a typical kinetic workflow looks like? So we start with a few experiments in batch reactors. In our case, we monitor by our process analytical technology. We get a number of data, could be spectra over time, could be images, could be a lot more. So these data are fed into chemometric models like the ones I described before, and together with solubility data that are fed to solubility models and particle properties that are offline determined. We can then add this data into crystallization process models, for instance, based on mass and population balance models. And through the solution of these models, we are able to estimate kinetic parameters for crystal growth, for instance, and monitor or model the supersaturation decay in time. So what do we do with this information? One approach is to do material classification, which will allow us to faster design processes. So material classification, for instance, we can classify different APIs based on their growth kinetic parameters. So this is a map we started to construct where the growth parameters are being plotted. And then you can see that some clusters are provisionally start to be identified. So at the end, we want to use this map to be able, when we have a new compound, to see where this fits and what is the similarity of the crystallization of the behavior of that compound compared to what has been crystallized in the past. So of course, if we want to have accurate crystallization kinetic models, we need to decouple the different rate processes. As I mentioned in the beginning, we have different mechanisms that could take place: dissolution, breakage, nucleation. So we can do different experiments to decouple these mechanisms, feed them into reduced models to determine the kinetic rate parameters, which are then are fed into a population balance model that describes the full behavior. So we've done this in some publication previously, but of course there's a large degree of uncertainty when you do these kinds of experiments in many instances. So what can we use these kinetic models as well? So we can also use those to obtain control trajectories. So we can use them to control crystallization. So if we have the kinetics available and the system is well defined, we can start asking what would be, for instance, the optimal temperature and dosing, antisolvent dosing trajectory to obtain a given development goal. And a given development goal could be how to maximize crystal structure, for instance, or maximize crystal size, excuse me, or to obtain a certain particle size distribution, but it could be other things, how to maximize yield or to decrease batch time, or it could be multiple objectives. So basically before we had data and we wanted to derive kinetics. Now we have kinetics and we want to get data. What are the conditions that are the best for our development purpose? This is an example of one of these applications where we looked into a combined cooling crystallization process. So for this case, we had crystal growth and nucleation kinetic parameters estimated, as shown here. There was also solubility model available based on the semi-mechanistic model that I showed in the beginning. So we wanted to obtain the temperature, the optimal temperature and antisolvent cooling trajectories to maximize the number average crystal size. Basically, in other words, suppressing nucleation and favoring the crystal growth. And this, of course, is subject to several constraints. So the max batch time should be satisfied. The dosing cooling rates should be what our plant allows, of course. So we calculated these optimal profiles. And interestingly, we saw that they're quite different from what is typically developed empirically. So in this case, for instance, the controller tries to keep the supersaturation constant to a certain degree where nucleation is prevented. So you see non-linear cooling and antisolvent dosing profiles happening simultaneously. So this is not what typically is developed empirically. So we can use this actually to also simulate the particle size distribution in time. And then we can use this approach to have a more of a model-based design of our crystallization, which is quite typically different from what is developed empirically. What is next in this approach? So we want to actually validate this for several compounds. This was just one example that I showed before. We also want to integrate online measurements, so size measurements, and eventually we want to close the loop for this in a model predictive control scheme. We have a collaboration with Process Systems Enterprise Siemens to look into these elements that have been demonstrated for some other processes. Another possibility is to use hybrid modeling, where we can combine mechanistic models with machine learning models. And the advantages of doing so is that often it could be the best of both worlds. Could offer the golden balance between accuracy and prediction. Computations can also be sped up, but we can also substitute for phenomena that are either unknown or quite difficult to assess, for instance, agglomeration and breakage. All right, so this brings me to the conclusions. So what I've shown here, so I've discussed solubility regression models. So we can use machine learning for solubility regression. The models that are obtained are accurate, but they're quite hard to generalize. But we think it could be, while they need more data, it could be the only way forward for some systems, especially when you're going to more than ternary solvent systems. I've also shown that we can use a statistical technique based on optimal experimental design that can reduce experimental effort by at least 50%. And this is a nice and generally applicable method. Next, I discussed chemometrics for soft sensor development. So treating output of process analytical technologies, even with simple statistical learning techniques, we can get very useful insights. But we've seen that constructing calibration models for this could take a lot of effort. While it works, it suffers from issues such as calibration transfer, hyperparameter tuning, different equipments, and a lot of other things. So it's labor intensive, but it works. And we also need more work on artificial intelligence and machine learning for accurate size description from image analysis. That's quite important for us. Then combining output of different PATs into one machine learning technique could also be something interesting for the future development of soft sensors. Finally, for crystallization process models, I've shown very briefly the development of crystallization kinetic models. We can use those for classifying materials, but more importantly, we can use those to develop open loop control trajectories, which can help us to optimize processes in terms of time, cost, solvent, or product properties. However, the kinetic and solubility submodels that go into this should be well described. And of course, to be able to predict size, this links back to the online size description from the images. That's quite important to be improved. All right. So with that, I'd like to thank you for your attention, and of course to give some acknowledgements here to the number of people in J&J and at the various academic partners that we work together, as well as Open Analytics, which help us with data science in this work. So thank you.
Christos, thanks a lot. As usual, a very rich and a very broad presentation. I like this style a lot. I think it was a great overview. Now we're, of course, a little bit behind schedule, but by 12 minutes. So I'd like to, well, we have time for one question, which you can read in the Q&A function. Hi, very nice presentation. I'm curious about the specific matrix of the Fisher information matrix that was used in the I optimal design as against the D or A optimal design criteria.
Well, we've looked into the D. Can you hear me still?
Yes, we can.
Yeah. Well, we looked into the D and even A optimal designs. So what was more interesting? So the D optimal design, for instance, is based on getting the most accurate parameters for the model, and that's quite important. For instance, if you want to extract physical properties from those parameters. However, the application we had was on an empirical model, or a semi-mechanistic model, where the parameters do not have a lot of physical meaning here. So that's why we apply the I-optimal design, which is based on let's say getting the most the better predictive power of the model. And that's, we found that this was the most interesting approach for our case. So we did screen these approaches as well, but of course, since they are not optimized for getting the best prediction, the best modeling prediction, they performed worse as compared to the I-optimal as well.
Okay, thanks a lot, Christos. I guess you're available. You'll be available for any offline discussions regarding the material you presented, as it was quite broad.
Yeah.
Okay, thanks again, Kevin. The word is to you.
Thank you, Christos. Very nice talk. Congratulations. And this brings us to our last talk. Last but not least. So last but not least, we have Professor Coley here. He obtained his Bachelor of Science in the California Institute of Technology. Also obtained his PhD in the Massachusetts Institute of Technology, where we got to know each other, and it's also there where he is a professor. He has won numerous awards, and one of them I would like to highlight, which is the Samsung AI Researcher of the Year in 2023. So this shows that he is one of the key guys in this area. I will not continue, Connor, but the floor is yours. I will want to leave as much time for you as possible. Good luck.
Thank you, Kevin. And thank you for the opportunity to share some of our work with you all today, and good afternoon to everyone listening. My research really focuses on the intersection between AI and chemistry. And so today we're going to be thinking about the use of AI in chemical synthesis planning as, given the topic of the session, a path towards process intensification. Now, the types of molecules that I think most about are therapeutic molecules. So these processes that I'm talking about tend to be manufacturing processes or synthetic processes to make active pharmaceutical ingredients. Now, process development in the development of a drug candidate is a quite involved process. It goes through many stages. It involves these sort of earlier ideation stages where you're sort of taking a molecule that you've already designed and validated some activity of, and you're trying to design a route that is suitable ultimately for sort of larger scale manufacture. And so from those initial ideation stages of mapping out possible routes, you can imagine going through different narrowing stages, maybe getting small bits of experimental information to select which ones are better or worse than others. Ultimately, you'll do some sort of proof of concept before moving on perhaps to a second phase of process optimization. Now, in the sort of process optimization phase, then you might be using techniques, as we've heard about today, from Bayesian optimization, as well as optimal experimental design. And that's more direct feedback between experimental evidence and process parameters. Now, in this talk, we're going to focus a little bit more on this earlier stage, that's sort of route optimization that starts with this sort of very early idea generation. Now, overall, if we're thinking about the use of AI for chemical synthesis, we should think about the different ways in which it can be used. I like to think about this in terms of different tiers or different ways in which we can use AI for synthesis. And the foundation of much of what we do is going to be data. It is accessible, searchable, fair data that tells us what's been done before, how well did it work, right? And really just what is the state of research in this field? For a given reaction type, can we survey the full spectrum of catalysts that have been used in the past? Now, it's on top of that data that we can start to build predictive models. And we can start to build different recommender systems that we interact with. They can provide feedback on sort of what our experiments are doing. They can suggest conditions to try, and they can help us troubleshoot when things go wrong. And ultimately, right, if these were to be sort of more mature, more precise, we might reach a state where we can use these models as complete digital twins and perhaps use them to coordinate autonomous laboratories. And so that's really the goal that we and many others are working towards when we talk about AI for chemistry. But of course, we're not quite there yet. So given this sort of foundational data and the information that we do about chemistry, if we're trying to develop techniques for planning chemical manufacturing routes, we need to first try to approach the task of retrosynthetic analysis. And for this, it's been the most common technique to define reaction templates. Now, reaction templates are these symbolic rules that codify some sort of rule of chemistry. They're the kinds of transformations that you find in books of named reactions. And we can encode them in different cheminformatics languages like SMARTS, and we can then apply them to new molecules of interest. And this approach can be very successful when you invest the time into curating and defining these sorts of rules, particularly if there's a small number of rules that you care about or a small number of reaction types that are relevant for the molecules you're trying to make. This is a great approach, but we can also take a different tactic in trying to learn these kinds of rules from data. Because fortunately, we do have millions of published chemical reactions from journal articles and from patents that give us information about what reactions have been run, how were they run, and what the outcomes were. And so we use this information to build models. Again, we have information about what a chemist has reported. It's been tabulated and curated in these databases like SciFinder and Reaxys and others. And while we don't have all of the information that we'd like, or we're missing certain procedural details, we do have still quite a bit of information to work with and to build our models with. And so we're going to take these reaction examples, these millions of reaction examples, and we're going to put together programs to help us plan syntheses. Now, one tactic is to build the symbolic rules that experts could define, but instead we're going to define from data. So we can look at published chemical reactions and we can extract out the symbolic transformation that captures the essence of that reaction. So this is an epoxidation, and we can learn this rule that says, perhaps this way of doing an epoxidation is general. And so if I'm faced in the future with a molecule that has this epoxide motif, perhaps I can use an epoxidation to access it. And so we can extract millions of these symbolic rules, or at least hundreds of thousands from our data sources. And then we train models to recommend their use. And so this was shown very nicely by Marwan Segler, right? We can train machine learning models to take a product that we'd like to synthesize and recommend one of the symbolic rules that we might be able to use to produce it. In this case, looking at this product, the model selects that rule that corresponds to a retro Bromo-Suzuki coupling. Now, because the sort of retrosynthetic step is really just a transformation from a product molecule into reactant molecules, we don't have to use symbolic patterns. We can use anything we like, right? Any model that can take a product as input and output one or more reactant molecules is fair game. And so borrowing other techniques from machine learning, there are plenty of architectures that we can use to convert between sort of string or language representations and smile strings of the product, turn that into smiles of reactants. There are graph translation approaches, and there's mixes of the two. And the whole idea is that we're just training deep learning models to take a product molecule and, based on what's recorded experimentally, propose that set of recorded reactants. And that's really the cornerstone of retrosynthetic analysis these days with data-driven techniques. We use these models to take a product of interest that we'd like to synthesize and find a suitable process route for, and it will recommend a disconnection. We then look at those molecules, and if those aren't purchasable themselves, we'll go further back and further back and further back, and we have this recursive tree search that we then conduct. Now, there's techniques, algorithmic techniques to mitigate the cost of this tree search. Things like Monte Carlo tree search from gameplay, algorithms that you might have heard about being used in chess or Go or StarCraft in reinforcement learning. These can all be applied to this problem as well. Retrosynthetic analysis is, in a sense, a one-player game. And it's been shown that the programs now are at a point where they can generate these sort of multi-step pathways that are in some ways competitive, or at least comparable to the pathways that would be proposed by experts. Now, where things get interesting is when you sort of recognize that retrosynthetic analysis, just taking a product and finding intermediates and starting materials, that's not enough, right? That might be enough for very early stage discovery, because discovery chemists in the pharmaceutical industry, right, are perfectly capable of filling in that missing information and understanding, okay, how should I run this transformation? They'll use column chromatography to purify things. But if you're talking to process chemists, as many of us do and will, they might be a little bit more critical, right, about what are the criteria that make a good synthetic routes, right? You don't just go into the lab and mix reactants together. You have to know conditions. You have to decide orders of addition, vessels. You should be concerned at some point about cost, purity, scalability, and in particular, purifications as well as this sort of additional step that we don't think about when we do retrosynthetic analysis itself. But it's a very important part of synthesis planning overall. Of course, if we're also then thinking about that eventuality where we're using robotics and automated labs, robots will need us to tell them exactly what to do, at least with heuristics or predictive models. And so we need much more precision in the details of these pathways. And so while we can do retrosynthetic analysis reasonably well, we now get into really the nitty-gritty of process chemistry. Now, at the most basic level, reaction conditions can also be thought of as a recommender problem. Right? In our data sources, we've got information about the conditions that were used for different chemical transformations. And so if we have a new reaction, just B plus C goes to A, we can try to query a model and ask it to recommend reagents, catalysts, solvents, and temperature, and we can train that model just by basically filling in the blanks. So we can take reactions that we've seen published, we can mask or remove those conditions, and we can train the model to reproduce those conditions. And this is actually a very nice supervised learning problem that we can then use a variety of approaches for. Now, beyond just predicting the identities of these agents, we can also try to predict concentrations and quantitative details. And so with these same data sources, we can train models that take in a desired reaction defined by the reactants in the product and recommend not just the species to use, right, but as you see here, the equivalence ratios normalized to some limiting reactants. And sometimes we're a little off, right? The experimental record here was in black, and so that's a 1.5 equivalence ratio approximately. We predict 1.25. Reaction would still probably work. And maybe we predict a slightly different way of achieving a similar catalytic effect and slightly different temperature. But by and large, these models can recommend quite reasonable conditions. And so this kind of capability and these kinds of predictive models are ones that we've been training for many years. We package them up and try to make them available through graphical interfaces as well as APIs in a tool that we call ASCOS. We re-released ASCOS in the fall. So now the sort of new open source version is much more maintainable. It's a very maintainable microservice architecture that folks can spin up or down individual components and models as they desire. And so if you are interested in data-driven synthesis planning, I'd encourage you to check out ASCOS. The code is available, and so you can also spin it up on your own behind a firewall, and so there's zero risk of information leak. Now, with ASCOS or other tools, because there are other tools, we might generate large numbers of ideas. So in this case, if we query ASCOS with this particular drug substance, we get this whole network of possible reaction pathways to produce this molecule. And each one of these might give us a different idea on how to achieve that structure. And so while it's fantastic to have many options and to have a program tell you that there are hundreds or thousands of possibilities, it also really increases the bar for ranking and scoring them. So given the sort of abundance of ideas of how we might access that structure, we really need to think about then ways of prioritizing. So what makes a good route? Right? This is really the heart of the question. What makes a good pathway to a process chemist? Feasibility, right? Maybe sustainability. We might want the yield of reaction steps to be high. We might want to avoid certain types of impurities. It'd be great if we can avoid complicated purifications and do this in one pot or telescope. But is it flow control? What's the cost of goods manufactured? Right, it's going to be scalable, automatable, and really there's an endless list of criteria that you could define for pathway ranking and scoring. So I'll just mention a couple of the approaches that we've been taking to some of these. It's a very daunting list and there's a lot of complexity. So we have to try to decompose those tasks into things that are actually tractable for us to learn. Feasibility is one that we've been working on for quite some time. Feasibility would just say, if I propose this reaction, I want to make a certain product, I've proposed some reactants and conditions to do so. Do I think I'm going to make that product? So we have models that can try to predict the products of chemical reactions, and they do this in a number of different ways. Again, using maybe spiles, strings, or graphs, or different representations of molecular structures from cheminformatics. We also think about green chemistry. In sort of green chemistry, some of the metrics that we can compute are quite simple, right? Given a proposed pathway, the atom economy, quite straightforward to calculate. The number of steps, quite straightforward. We can favor the use of bio-derived building blocks over petrochemical building blocks. We can use traffic light systems from, let's say, GSK to evaluate the greenness of different solvents and reward things like water and ethanol and penalize things like chlorinated solvents. We can even estimate process mass intensity. It's a very crude estimate, admittedly, but we can try to estimate the overall sort of mass of inputs to our process and compared to the mass of outputs, at least on the synthetic side if we ignore purifications. And what's more is that these metrics don't just have to be used for scoring a pathway. We can also use them in the search process itself and use techniques like reinforcement learning to train agents to find us pathways that are more green than the ones that they would normally find. Now, I already sort of indicated the fact that of these process metrics, things can get quite complex. So if we even take sort of one particular example, just cherry picking, the ability to telescope a reaction pathway or perform it at one pot without intermediate purifications, or what does that actually take to assess? If we're trying to build an AI model or program to help us assess this, what does it need to do? Well, of course, we need to know what conditions might be appropriate for each reaction step in a process. We need to understand the solvent compatibility, right, between consecutive steps if we're not doing any sort of purifications. After the first reaction step, we're going to want to know not just the major product, but the full distribution of products, their yields, precise amounts, because we need to be able to then predict how will those side products or byproducts impact the next reaction step. As we keep going in a synthetic pathway over multiple steps, how are those going to propagate? And ultimately, right, maybe there's a final crude product mixture, and we'll need to understand how we might purify the actual product of interest. And so this is, just sort of one criterion that we could consider for evaluating and ranking pathways, and yet there's this enormous amount of complexity built in. And so we try to make some progress, right, on these tasks, but of course, it's very much an unsolved or open challenge. Impurity prediction in particular is an interesting one. And so one of our approaches to impurity prediction has been teaching models to think in terms of mechanistic steps, elementary reaction steps. The thought is that impurities form by the same physical processes as the major products, but they might have different product channels and branching points. And so we can train machine learning models to take reactant structures and predict, in a mechanistic sense, what might unfold in that reaction flask. And we're simulating basically what is happening inside the flask and what are the final products or sets of products that might be observed. But impurity prediction is really just one of the many, many challenges for this task. And really, when we think about sort of condition prediction more holistically and trying to understand, okay, how will different aspects of the conditions influence the outcomes, we don't actually have great solutions, right? Just be very transparent about it. We can take a recommended reaction and try to infer or predict what catalysts, solvents, and reagents to use, the temperature as well. The concentrations and reaction time is still something that we're working on. But we can't predict in a data-driven manner what kind of reaction flask needs to be used or how it needs to be prepared. I don't have a model that can say, do you need to oven dry your flask before the reaction or not? We don't have a model that says what order to add species in. We don't have a model that says whether the rates of addition matters. And for multi-step sequences, we don't have models that tell you what or how to run purification steps. And so there's really an extraordinary amount of complexity in process design that we're only beginning to scratch the surface of with these data-driven techniques, right? There's no equivalent of Aspen for process simulation that applies to pharmaceutical manufacturing, as far as I'm aware. And really, this is the heart of the challenge, is that we cannot predict the full procedural details at the moment or anticipate how those procedural details would affect reaction outcomes. And so in part of my own past research as a student still working with Janssen and others, this sort of gap or this divide between what we're able to plan and predict with data and machine learning and what it actually takes to run a chemical reaction in the lab was sort of the source of a lot of challenge. There was a necessary human refinement step in the middle of this otherwise automated process. So this was a demonstration trying to use AI to plan processes for robotic flow synthesis. But we still relied on experts to help us do the practical steps of preparing stock solutions, but also to try to ensure that things would stay in solution, specifying concentrations and residence times, and understanding if we can telescope unit operations. And this connects back to Martin's mentioned earlier today about property prediction as really a cornerstone of reaction engineering. Christos also talking about sort of solubility, right? Especially for assessing compatibility and flow. These are essential considerations. And actually, in flow chemistry, if we're thinking about process intensification, it behooves us to run at concentrations that are as high as possible. But of course, the higher the concentration, probably the closer you're going to be to hitting some solubility limit, either for your starting materials or an intermediate or your products. And so it's this sort of dangerous game where we can't predict concentrations with enough precision to know how close to the operating limit we can operate. So there's still some balance between what we can predict with AI and what requires empirical experimental evidence. And part of why AI has this, finite set of capabilities is because of the data, right? The data sources that we use really influence what we're able to do. And the data that we learn from tends to either come from the literature, which is very diverse with respect to reaction types, but not diverse with respect to conditions, or it comes from high throughput campaigns, which are basically the converse, right? So they're very rich in changing categorical reaction conditions, but we only have high throughput experimental data for a small number of transformations. And so perhaps, right, there are opportunities to generate data more sort of in this sort of magic spot here, where we have diversity along both axes. And this is, one of the sort of goals indirectly of an effort I'm involved with called the Open Reaction Database. So the Open Reaction Database is trying to change the state of data sharing in synthetic organic chemistry in support of many of these downstream machine learning tasks. And so I'll just close in summary, back on sort of this list, just thinking about really the landscape of all of these considerations that you could impose when thinking about what a suitable process route is, right, on this path to process intensification. As I mentioned, we're only really scratching the surface on a few of these. Some of them we can build heuristics for, some of them we're building models for. But really, if you're interested in this space, right, there's tremendous opportunity to improve our ability to score and evaluate hypothetical synthetic pathways on the basis of these criteria. And so I think this is where, again, the main opportunities are. Now with that, I'll go ahead and thank you for your attention, and I'll thank obviously an excellent research group here at MIT that conducted all this work, as well as support from our funders. And would be glad to take any questions if we have a few minutes left in our time today.
Thank you, Connor. Thank you, Connor, for an excellent and a very clear talk. Maybe start with indeed some general questions, and I see two of them. And then the chat is that as a chemical engineer, we are not always trained on using AI, or in how would you, as a recent graduate, and what advice would you give him to a recent chemical engineering graduate if you want to pick this up? How would you start?
Yeah, that's always a really good question to ask and to consider. So I've always been of the mindset that having background in the domain of chemistry or chemical engineering is a strength, because it really helps us know, okay, what problems are worth solving. I think this is something, there's a lot of problems out there that you can solve with AI and machine learning, but the ones that are worth solving are the ones that are worth solving regardless of whether you're using AI or machine learning at all. And so I think having this sort of understanding of what the real challenges are in the fields should come first. And then we can start thinking about, okay, well, what are now the techniques and the toolkits that might apply from AI? At this point, my recommendation would probably be thinking about some of the general introductory material that's out there, Coursera courses of Intro to ML. These provide sort of good foundations of notions of, what is supervised learning, what is unsupervised learning, what is generative modeling. And then I think for chemistry, in particular, one of the sort of backbones of what we do is use graph neural networks. Graph neural networks came up earlier today as well. And so I would really think about just sort of reading some recent articles from groups like the ones that you've heard from today to see what are the kinds of models that are being used, right? What are the types of representations, the types of models, and the best way to learn from my experience is just to start tinkering. Open up a Google Colab notebook, which will run in the clouds, give you this sort of free notebook-like interface to GPU training, and it's a wonderful place to start.
Okay, great.
Can I ask
sure.
something on this slide? I'm very, Connor, thanks a lot for the presentation. It was very, very informative. Looking at this slide, right? And looking, I see you say, let's say that I want to produce a particular molecule. There are hundreds of possible chemical routes to get there. Those have to or can be evaluated on a series of criteria that you have on the left-hand side of the slide. But if you look at these criteria, several of them are usually or more reliably evaluated not at chemistry level, but at process level or plant level. For example, the greenness criterion or the cost. These two are usually evaluated on plant-wide level. Also, the yield or the purity. These do not only depend on the exact chemical route, but also on the technology that is used. For example, a particular chemical route might be suitable to be performed in a membrane reactor, another one not. The membrane reactor, if it works well, will give a higher yield and a higher purity. So can you please comment on that? Also, the scalability criteria, how does this depend on the exact chemistry, on the chemical route? How?
Yeah. I mean, it's a perfect question, right? So a lot of the criteria that we would use, thinking more about sort of process and at-scale manufacturing, are things that require additional specification. And so, when sort of I showed this slide talking about how retrosynthesis is not enough, and I said, well, you at least need to fill in conditions. There's this one arrow on the right side of the screen, but there's probably a dozen arrows, right? Mapping the chemistry to hardware, understanding how that hardware fits into a plant scale, because absolutely a lot of the considerations of actually having precise estimates of cost, performance, etc., do rely on the mapping of the chemistry to the hardware. And so that's an additional step that one could view as a recommendation, as an inference step. When I think about how to sort of approach these criteria in a somewhat hardware agnostic way, I think the question that I would ask is not necessarily what is the precise cost, because that requires knowing the hardware. Maybe what's a ballpark cost, assuming that I make reasonable choices as to the hardware. But you're absolutely right that there's a lot of sensitivity to other decisions that I didn't even really mention in this talk that are essential, especially as chemical engineers, to consider.
Okay, many thanks, Connor.
Yeah.
Very interesting.
Yeah, one last question, because I see people are still staying, so this means that they're still interested. What do you expect for the next step for ASCOS? Then, what do you see there?
Yeah, I think with ASCOS, I think we are trying to improve sophistication in two directions. So there's still challenges in using data-driven programs to predict, on the retrosynthesis side, very complex natural product structures requiring many more steps than some small molecule APIs. So we're trying to push both the complexity of structures that are addressable with retrosynthetic analysis, as well as some of the things we've just been talking about of how to evaluate proposed pathways in terms of more sort of nuanced considerations of process chemistry. But our hope, because ASCOS is open source, it's a very scalable platform. Our hope is to have contributions also come in from folks in the community. And so I hope many people will see ASCOS as a platform to build upon themselves and to contribute some of these additional predictive modules.
Okay. And I think Georgios, we can close. I think Connor, thank you for this excellent talk.
Thanks so much.
Thanks to all the speakers and for your audience for the very good questions. There are still some questions in the chat. Something on a process simulator for pharmaceuticals, so that could be of interest. So Connor, maybe if you can take a look at the chat, this seems to be very interesting. Yeah, so I think we had a great session. Thanks to all the speakers. Thanks to Martin. Thanks to Georgios. So I think we can close.
Yes.
Thank you all. Have good evening. Bye bye.
Bye bye. Bye.
Thank you all. Bye.